Okay, physical science. Let's look at chapter 7 and 8 to prepare for this test. And all I'm going to do is I'm going to walk through some of the main topics of each chapter. And as we do, you can be writing this down on your study guide. And I'll give you some examples as well as we go through these topics. Okay? So chapter 7 was all about reactions. And we just want to remind ourselves some of the basics about a chemical reaction, some of the parts of the chemical reaction, how to balance a chemical reaction, etc. So let me just give you an example here, and then we'll kind of define some things concerning a chemical reaction. So we've looked at this reaction before. We have hydrogen gas and oxygen gas combining to produce water. And you have to know that the species, the compounds, whatever you want to call them, the elements on the left side of the arrow here are going to be called our reactants. So you must know that hydrogen and oxygen are the reactants. Anything on the other side, the right side of the chemical equation, this chemical equation is describing a chemical reaction. These are our products. Okay? We talked about this arrow here, meaning that a chemical reaction is taking place. You might replace that arrow with the term yields or produces. So we could read this as hydrogen gas reacts with or is added to oxygen gas to produce or yields water, H2O. And we might also put some symbols here like L would be for liquid, G would be for gas, and if you saw an S would mean solid. And if you saw an AQ, that would mean that it is dissolved in water. It means aqueous. Okay, dissolved in water. We talked about the fact that in order for this reaction to occur, on the reactant side, this is where bonds are broken. And on the product side, this is where new bonds form. Okay? So reactant bonds are always broken. That requires energy. So energy is absorbed. Energy needed to break bonds. And over here, energy is released. Energy released when new bonds form. Okay? We also mentioned that the overall reaction could be endothermic or exothermic. What that means is if it requires more energy to break the bonds than the energy released, then more energy is absorbed than released. Okay? So what that means is this. Oops, sorry, that should be a line right there. So it is going to be exothermic reaction, an exothermic reaction if energy released is greater than energy absorbed. Okay? So if the new bonds release more energy than the energy needed to break the reactant bonds, then the overall reaction is going to be exothermic. So energy is going to be released as a result. And you're going to see energy could be written like, there could be a number over here, like plus 315 kilojoules or something like that. That means energy is on this side and it's being released, it's being produced. Okay? It is endothermic if energy absorbed is greater than energy released. Okay? In this case, what that means is in order to break these bonds, more energy is needed to break these bonds than the amount of energy that is released when these new bonds are formed. So in that case, you would not see the energy value on this side, you would see it over here on the reactant side, so like 315 kilojoules or something like that. That means that it's endothermic. That's how much energy is being added in order for this reaction to occur. Okay? So if the energy value is on the reactant side, that means it's endothermic. If the energy value is on the product side, as I showed it over here, that means it's exothermic. Okay? But please realize that it always takes energy to break the bonds. Energy is always released when new bonds are formed. You're just comparing the two, which is bigger, and that's going to determine whether it's exothermic. It's exothermic if the released amount is bigger than the absorbed amount, and it's endothermic if the absorbed amount is bigger than the released amount. Okay? All right. So that is dealing with reactants there. Okay? And we talked in length about reactants. We did a lot of examples of reactions in our lab, in our classroom, and we talked about exothermic and endothermic, so hopefully this is a nice review for you. Okay? All right, we also looked at the law of conservation of mass, and that is that we have to balance these equations, okay? So don't forget that the law of conservation of mass basically says this, that the mass of reactants has to equal the mass of the products. You can't create or destroy matter. What you start with has to equal what you end with in terms of the mass of the two sides of the reaction. Okay? And that would mean that we have to have the same number of particles of each element on the both sides, and that's why we balance it. Okay, so this leads us to the balancing of equations. And I'll give you an example. So let's take our equation right here again. H2, this is gas, hydrogen gas, and oxygen gas are going to combine to give us liquid water. Now, if you look at this, this is not balanced, meaning we have too much of something on one side and not enough of it on the other side. So let's look at our elements here and see what the case is. So you take each element individually and you look at it and say, okay, this is the correct formula for hydrogen gas, H2. That's how it appears in nature. So there are two hydrogens here bonded together like that, and here's oxygen gas. It is also two oxygen atoms bonded together. Over here we've got water, and it is an oxygen with two hydrogens. But you'll notice that we've got two oxygens on this side, but only one on the other side. That can't happen. So the way we fix that is we use large numbers that go in front of the compound. Don't change the formula. Never change the subscripts. Never change the small numbers. Once you have the correct formula, you're done with the formula. I have to then get twice as much oxygen on the product side, and I do that by putting a large 2 called a coefficient. That big number is a coefficient. I'm going to double the number of water molecules. It must mean that I'm going to form 2 water molecules like this. Now I've got my 2 oxygens. These oxygens, that bond is broken. One of the oxygens goes there, one of the oxygens goes there. But you'll notice that I have now 4 hydrogens. 1, 2, 3, 4. Well, I can fix that by doubling the number of hydrogen molecules over here by putting a big 2 in front of that. So I have 2 hydrogen molecules. That's a total of 4 hydrogens. And you'll notice then, what does that mean? That these 2 of them go to one water molecule, 2 of them go to another, and that's how we get our 2 water molecules. An oxygen from here, 2 of the hydrogens makes one water molecule, another oxygen, and 2 of the hydrogens make the other water molecule. Now it's balanced. We've conserved mass, we've conserved the number of particles of each element, and we call that a balanced equation now. You use the large values in front of the compound to get the balanced equation. Okay? Let's look at another example here. Let's take, for example, nitrogen, hydrogen, forming ammonia. Okay? Now right away, if you look at this, you can see that there's two nitrogens on this side, and there's only one on that side. So I'm going to double this entire compound there. That gives me my two nitrogens on both sides. But also, if I double this, that just doubled the number of hydrogens. I already had 3, but now I just doubled that, so now I have 6. Can I get 6 on the other side, on the reactant side? Sure. I have 2 here, so I'm going to triple that. 3 times 2 gives me my 6, and now it's balanced. So you just check to make sure you have the same number of each element on both sides. Okay? Let's look at another example. Let's say I have magnesium and hydrochloric acid, and we're going to form magnesium chloride. That's the correct formula for magnesium chloride, and hydrogen gas. So I look at each element. Here's magnesium, Mg, and there's an Mg on that side. Great, balanced. Here's an H, but there's 2 H's there. So I need to double that compound. Now let's check the chlorine. This 2 also doubles the chlorines. So I have 2 chlorines on this side, and I have 2 in that single compound. So everything is balanced. Okay? We'll do one more. Let's take magnesium again, sure. And we'll go with sodium oxide. Okay? And let's say the magnesium kicks out the sodium and leaves it like that. Okay? And that would be, yep, I think that's right. This one's fairly simple. You'll notice we have magnesium on both sides. We have an oxygen on both sides, but we've got 2 sodiums here and only 1 there. All you have to do is put a 2 in front of that, and it's balanced. Okay? So, balancing chemical equations, you have to be able to balance chemical equations, get the same number on both sides. Okay? All right, then we looked at types of reactions, and we categorized them into 5 types. So the first one that we talked about was called synthesis or combination, and that is when you have just one product. So this one up here is an example of synthesis, forming the water from hydrogen and oxygen, just one product. Okay, one product. If you just see one product, that means you have a synthesis reaction. We talked about decomposition. Okay, decomposition means you have one reactant, and that one reactant is going to break apart into 2 or more products. All right, so that would be something like if you had magnesium oxide and that broke apart into magnesium and oxygen. We'd have to balance that like that. So you have one reactant breaking apart into 2 things, or 2 or more. Number 3, we talked about single replacement, or maybe called single displacement. And that is when you have one element replacing another. So you would have a single element on the reactant side and then a different single element on the product side. That's what we have here. We have single magnesium all by itself, and it reacts, kicks out the hydrogen, and now you have the hydrogen all by itself. That is an example of single replacement. Okay? Number 4 was a double displacement, or double replacement. And this is where you have 2 compounds and they switch places. The metals or the cations, okay? 2 compounds and the metals switch. So that would be like this. Let me give you an example. That would be like if I had something called sodium hydroxide and hydrochloric acid, and now the hydrogen is not a metal, but it's acting like a metal, but you'll notice that the first part of these 2 compounds, they're going to switch places. And what's going to happen, we're going to get sodium chloride, which is salt, and H and the OH come together, and that's just water. But this is a switch. The sodium is now with the chlorine, sodium chloride, and the H went with the OH to make what is essentially water, H2O, two H's and an O. Okay, so this is a switch of the first part of the two compounds, and that is a double replacement. And then the fifth type that we talked about was combustion. I think you guys enjoyed the combustion. Okay, and this was a hydrocarbon, like methane has to have carbon and hydrogen in it, and it combines with oxygen, it burns, and it always is going to produce carbon dioxide and water. So you need to know that any hydrocarbon, a hydrocarbon has carbon and hydrogen in it, you burn it in the presence of oxygen, you'll always produce carbon dioxide and water. Okay? Okay, after reactions, types of reactions, balancing reactions, we did all of those things. Okay? We also looked at exothermic and endothermic. We covered that. Okay? Okay, we also then talked a little bit about how can we increase the reaction rate. So if you remember, there are a few things that affects the reaction rate. Okay? The rate of the reaction, remember we can heat it up. That speeds up the reaction. 2, we can add more, we can increase the concentration. Okay, you're going to have more collisions. So heating it up forces them to collide with greater force. Having a higher concentration is going to mean you get more collisions. Okay. You could agitate it, stir it. Remember we talked about that. You want to mix them better. We also talked about the fact you could increase the surface area. Remember we crushed it into a powder. Okay. And I'm going to add another one here, and that is a catalyst. A catalyst is another chemical that speeds up the reaction, but it's not going to be consumed. It's not going to be used in the reaction. It just helps the reaction occur. So just know that a catalyst can speed up a reaction. Okay? Okay, so that basically is what we talked about with our chapter 7, about reactions. We looked at what a reaction is. We talked about reactants and products, that bonds are broken, new bonds are formed. We talked about exothermic and endothermic. We talked about balancing, conserving the mass. We talked about types of reactions and then speeding up the reaction rate. Okay, so that is chapter 7, and hopefully this helps you a little bit with your study guide, and we'll do some more examples hopefully in class to go over these and assist you a little bit. Okay, so chapter 7, make sure you know all about the reactions to get ready for the test.